All right, so next we're going to take a look at some really basic general chemistry and a little bit more on some biochemistry relating to some things we're going to see in this course. And so this is going to give us a little bit of a foundation for what's going to be coming up in the upcoming chapters. So this outline kind of shows us what we're working with here. We're going to start off talking about atoms. From there, talk about different types of bonding, ionic bonds to some degree, but especially covalent bonds, both polar and nonpolar covalent bonds, and see how that contributes to water, which actually is a really unique substance that gives life many of the properties that it has. We're going to take a look at some pH, and then we'll take a look finally, the last half of the chapter roughly is based on some different types of organic molecules. And so from there, we're talking about things like proteins, nucleic acids, lipids, and carbohydrates. And so there's some similarities there we'll see among those different types of macromolecules, and also obviously some differences in terms of what they do and how they affect living organisms. All right, so like I said, we're going to go all the way back to basics here and talk about what atoms are, and then from there start talking about what happens when atoms start to interact with each other. Right, so matter, which is anything in the universe that has mass and takes up space, is composed of atoms. And so looking at the structural features of the atom is going to tell us something about how matter behaves, and in particular how living things interact with their environment and how they maintain the kinds of processes and reactions that go on within their cells and within their bodies. Right, so the basic composition or makeup of an atom is made up of protons, which are the positively charged particles, neutrons, which are neutrally charged, neutrons have no charge, and electrons, which have a negative charge. And so in particular, the nucleus is going to provide stability to the atom. It's going to give us the atom its identity. As we'll talk about later on, I think about proton number, and the nucleus is made up of protons and neutrons. I think of proton number as being the identity of the atom, whereas the electrons are more the personality of the atom. So that's going to give us some indication or a prediction of how particular atoms are going to behave when they're around other atoms of similar types or even of different types. So the electrons in particular in biology are the really interesting part of things. They're what determines how reactions happen. They're what determines how different kinds of things interact with each other. So we're going to tend to focus more on electrons more than we are either protons or neutrons in this course. Right? So like we said before, protons and neutrons are in the nucleus, and electrons are somewhere outside the nucleus in space. We're not going to talk too much about where these are positioned and how we know that and how they kind of move around the nucleus, but they are located outside the nucleus. So two relatively simple elements here that are made up of atoms. Two very important ones from a biological perspective are hydrogen and oxygen. Hydrogen is made up of a single proton and a single electron, no neutrons. And oxygen is made up of 8 each, protons, neutrons, and electrons. And so based on that, that's going to tell us something about how these different elements behave, how they interact with other elements, and that will help us, like we said before, understand how interactions occur in some types of living systems. A molecular formula is used when we're trying to figure out how different groups of atoms are associated together. So a molecule then is a group of atoms held together in some type of stable association. O2, for example, is an oxygen molecule. The smallest molecule you can have is made up of only 2 atoms, like O2 or N2. Right? So those kinds of things are made up of 2 atoms, but since they have 2 or more, they are considered molecules. And this bullet point says that they're covalently connected. We haven't really talked too much about what that means. When we say covalently, that's a type of bond. And this type of bond in particular is going to consist of an even sharing of electrons between the 2 oxygen atoms. And that even sharing is going to give oxygen some very important properties. It's possible with some molecules that when they enter into this covalent type relationship where they share electrons, the sharing might not be even. And that's going to give those kinds of molecules some other important properties as well. In particular, those kinds of things are going to interact with water, whereas these kinds of molecules, where the sharing is equal, are going to have a very different kind of interaction with water. So if you were to have 3 O2s, that's the same as saying you have 3 molecules of oxygen. So in total then, if you have 3 molecules, and each molecule consists of 2 oxygens each, 3 times 2 is 6 oxygen atoms together in that 3 molecules of O2 gas. 6 molecules of water, kind of the same thing, right? So if we have 6 water molecules, each one is made up of 1 oxygen and 2 hydrogens. If you have 6 molecules of water, you actually have 12 hydrogen atoms and 6 oxygen atoms. Right? So we work with these molecular formulas. It's a very convenient way of using shorthand to kind of save us some time and energy and space when we're trying to write about these different kinds of things or even talk about these kinds of things. Now, in general, at least on the periodic table, the elements that show up in the form that they are in the periodic table are neutral. meaning that the number of protons is equal to the number of electrons. Now, that isn't always going to be the case. There might be cases where one particular substance might have more electrons than protons, or more protons than electrons. And when we get into that type of situation, we're going to have what are called ions, right? But for the most part, at least in terms of what shows up on the periodic table, there is a no net charge on those different atoms on the periodic table, since the number of protons is balanced by the number of electrons. The number of pluses is balanced by the number of minuses. That means that the elements are going to have a neutral charge. So an element then is a substance that cannot be broken down into simpler substances using normal chemical means. It's not that it's not possible to break them down, but using normal kinds of techniques that we have available to us most of the time, elements are about as simple as you can get. You cannot break them down into smaller components using normal day-to-day kinds of means. So as far as different kinds of elements, we've already seen a couple of them, right? We've seen oxygen, we've seen hydrogen, we're going to see nitrogen and carbon as well. Those are kind of the four big ones in living things, C, H, O, and N. But there are several other 100 or so elements that show up on the periodic table that we could talk about as well. We can also talk about state phases. So all the different elements can exist in different state phases where they are solid, liquid, or gas. Depending on the pressure and temperature those elements are in, they can occur in different state phases. And so we'll see a few cases where that's important as well. That's not necessarily so much of a big factor in living systems. Like gold, which is Au on the periodic table, is also an element. And so it's about as simple as you can get. You cannot break it down further using normal chemical means. You can change the state phase, however, from solid to liquid to gas if you heat it up, or from gas to liquid to solid if you were to cool it down. So it is possible to change the state phase, but when you do that, you still maintain the identity of that same element. Now, isotopes are a different situation, right? A few minutes ago, I mentioned the idea of an ion, and we'll get back to those as well. But an ion having a different number of protons and electrons and therefore having a charge is different from an isotope. An isotope is where you have a different number of neutrons in a particular element. So for example, carbon can exist as carbon-12, carbon-13, or carbon-14. The difference between carbon-12, 13, and 14 is the number of neutrons present in those different isotopes. The proton number stays the same, 6. The electron number stays the same, which is also 6. But the neutron number can change to 6, 7, or 8, depending on which isotope of carbon you have in front of you. Right? So in nature, there are about 90 different naturally occurring elements. And so there are others that are man-made, but as far as naturally occurring substances that we know about, there are about 90. Of those, only 12 are found in large quantities in living things. Right? So the 12 we have up here on the screen: carbon, oxygen, hydrogen, nitrogen, sodium, chlorine, calcium, phosphorus, potassium, sulfur, iron, and magnesium are the 12 main ones that we find in living things. There are other elements that show up in smaller quantities, like selenium, for example, shows up in very small amounts in the body. Iodine shows up in very small amounts in the body as well. But of the really main substances that our bodies use, it is these 12. And really, if you want to focus that in even more, it's the first 4 on that list. Carbon, oxygen, hydrogen, and nitrogen are the main 4 that we find in living systems. Right? So if we look at those 4 elements, carbon, hydrogen, oxygen, nitrogen, that makes up about 96% of us by weight. So it's a huge proportion of the human body is made up of carbons, oxygens, hydrogens, and nitrogens. Hydrogen and oxygen you can see in water, and a lot of our body is made up of water, but they also consist or make up components of other things like proteins and carbs, and various other organic molecules as well. Nitrogen shows up in proteins especially, although it can show up in other places as well. It's really a big component of proteins. Carbon shows up in all the organic molecules, so those are kind of our big 4 when it comes to living organisms. Right? So if we look at the periodic table and we pick an element like oxygen, blow that up, we see that oxygen has what's called an atomic number up here on the top of 8, and an atomic mass down here of what we're going to call 16. Right? So what that means then is that oxygen has 8 protons. The atomic number is the same as the proton number for that element. And that element will always have that same number of protons. The number of protons for an element is a fixed number. It does not change. If you change the proton number, or if you change the atomic number, you change the element. Right? So if you have oxygen with 8 protons and throw an extra proton on it, you don't have oxygen anymore. You now have fluorine. Or if you have oxygen with 8 protons and you take one away, you don't have oxygen anymore. Now you have nitrogen. Right? So you change the identity by changing the number of protons. Atomic mass is something different. Atomic mass is the combination of protons plus neutrons. So in this case, oxygen has an atomic mass of approximately 16. We know 8 of those are protons. That also tells us then that there are 8 neutrons also in that atom of oxygen, because we know that 16 minus 8 is 8. You might be wondering about electrons. Well, how come they don't factor into the atomic mass? And that's because electrons are relatively small, so small in fact, they really don't contribute much in a substantive way to most elements' mass, or most atoms' mass, unless you start talking about some really, really large elements. They're not going to have a big contribution at all to the overall atomic mass. We don't include those, right? But in general, again, on the periodic table, because we know the proton number equals the electron number, just by looking at this box on the periodic table, we know that oxygen has 8 protons, and for that reason it must also have 8 electrons, so it's balanced, no net charge overall. And since the atomic mass is 16, the overall protons plus neutrons is 16, we know we have 8 protons. 16 minus 8 gives us 8 neutrons as well. All right, so the atomic mass is a feature of a substance which tells us how much of something there is. It's a little bit different from atomic weight, which is also used sometimes interchangeably with atomic mass, but really shouldn't be. Weight is contingent upon gravity, right? So for example, on Earth, you might weigh a certain amount, but on the moon, you might actually weigh less. Whereas mass is the same regardless of where you are, right? So if you're on the moon, on the Earth, on Jupiter, the mass is going to be approximately the same thing because it's less reliant on gravity. So if we take a look at titanium, titanium is number 22 on the periodic table, so that gives us a couple of important bits of information right off the bat. We know titanium has 22 protons and 22 electrons because the atomic number is 22. And the atomic number is the number of protons in that particular atom. Since the number of protons equals the number of electrons, we know that means there's also 22 electrons present in titanium most of the time. The other number, which is the atomic mass, is approximately 48, which means that if we take 48 minus 22, the total protons plus neutrons, minus the protons, that's going to leave us with 26 neutrons. Okay? And so for titanium, most of the time, 22 protons, 22 electrons, and 26 neutrons. And we get all of that just by looking at the periodic table. And so the numbers that come into play here are based on a unit of mass called a Dalton. So protons and neutrons are assigned a mass of approximately 1 Dalton. Electrons are not really assigned much of a mass at all, so we kind of leave them out of the equation. But that lets us figure out what the atomic mass is for any given substance. Like we said before, isotopes are things that have different numbers of neutrons than other versions of that particular element. I talked about carbon before as an isotope, carbon 12, 13, and 14. We can also look at hydrogen. There are different isotopes of hydrogen. You can have elemental hydrogen. You can have what's called deuterium. You can also have what's called tritium. And they all are versions of hydrogen that just have different numbers of neutrons than the other isotopes of that particular element. Some of these are also radioactive. And so things that are radioactive tend to break down or decay spontaneously, and in the process they also give off energy. And sometimes that energy can be kind of harmful to living things, which is why we try to limit our exposure to most types of radiation. Half-life is a good term to know about when you're talking about radioactive things. Half-life just means how much time it takes for half of a given substance to go away or decay, and therefore you have the other half left. So for example, if the half-life of a substance is 1,000 years, and you start off with 1 gram, if you come back after 1,000 years, you're going to have half a gram. If you were to come back 1,000 years after that, you'd have a quarter of a gram, because of a half is a quarter. If you were to come back 1,000 years after that, you'd be down to an eighth, and then a 16th, and then 1/32nd, and 1/64th, and so on of a gram for every half-life that you wait. Isotopes are really important when it comes to certain types of medical studies, scans, and so forth. It's also very important when it comes to ecological studies, where people track the movement of different isotopes through the environment as different organisms move, for example. So you can actually track migration of animals based on isotopes they pick up in their bodies in different parts of the environment. Right? So just to kind of recap a little bit, we know that proton number is a fixed number, a fixed identity or facet of any given element. Electron number is changeable. You can change the number of electrons in an atom, that's possible. And you can also change the number of neutrons in an atom. Right? So for the changing number of electrons, that gives us ions. Changing number of neutrons, that gives us isotopes of these different elements. Right? So I mentioned the isotopes of hydrogen a second ago. Elemental hydrogen has a single proton, a single electron, and no neutrons. If you look at deuterium, which is slightly radioactive, you have 1 proton, 1 electron, and now 1 neutron. So 2 particles in the nucleus, we call that deuterium. Deutero refers to second, or 2 of something. Tritium is 3 of something, so now we have 2 neutrons and 1 proton in the nucleus. So that's going to give us a slightly different isotope of hydrogen, which is tritium, which again is also radioactive and decays at a certain fixed rate. All right, so we're going to take a break there and come back and pick up the next section and start talking about electrons, which is a very, very important part of the atom, especially if you're a biologist.